Hey there guys, Mr. Carlson here. Let's take a look at this example where we're dealing with friction on an inclined plane. I've got a 45 kilogram child here that is having fun going down this slide. They tell us that the slide makes a 27-degree angle with the ground here. And the question says, if the slide is 5 meters long and she starts from rest at the very top here, how fast will she be moving when she reaches the bottom of that slide? Well, as always, whenever we're dealing with problems like this, the first key is going to be drawing a quality force diagram. So I'm going to first just label kind of the forces that I've got going on for this child. So the first thing, as always, we always know this, we've got gravity happening, and gravity is going to be pulling straight down like this. So we've got force of gravity here. We also know that make a dot here, in problems where we have inclined planes, that gravity is going to be broken up into two different things. So gravity is going to be doing two things. The first thing that it's going to be doing is it's going to be pulling, kind of trying to draw this parallel, but it's working out not to be very simple, straight down the slide. So gravity is going to put a force that pulls the child straight down parallel to the surface of the slide, and then gravity is also going to be pulling perpendicular to the slide like this. In other words, holding the child to the surface of the slide like that. So gravity is doing both of those things. It's pulling against the slide this way and pulling down the slide this way. Right? So this is being broken up into those two components, and we can label that force of gravity. We'll call this one the perpendicular because it's perpendicular to the surface of the slide here. And this will be the force of gravity that is parallel because it's parallel to the surface of the slide. Now we also have the normal force. Now the normal force, we've learned, is always pointing perpendicular to the surface that it's in contact with. So the child's in contact with the slide this way, and so the slide pushes up perpendicular to that. So that's the normal force from the slide. And then we also have, since we're told not to ignore friction, and in fact, we're given the coefficient of friction right here. That's what that mu symbol stands for. So 0.23 is the coefficient of friction. So we know there is some force of friction then of the slide pushing back against the child as they slide down this way. All right, so there's my force diagram. Oh, one last thing. Remember that if this is our angle here, 27 degrees, that means this angle between the perpendicular component and gravity here, that's 27 degrees right there. So now we've got all of our forces labeled on here. Let's see if we can't actually calculate the amount of some of these forces. Well, we know that for gravity here, and I'm going to actually draw it over here real quick so I got a little more room to write. So I'm just going to kind of draw, here's the normal force. I'm just redrawing this, I'm just moving it over basically. Force of gravity pulling straight down. This is pulling down the slide, that's force of gravity parallel. This is force of gravity perpendicular. And we've got friction this way. Okay, just to give myself a little more room to write. Well, we know that for gravity here, that's going to be 9.8 times that mass of the child, 45 kilograms. And so that works out to be, if I did 9.8 times that, we're going to get 441 newtons. So now I know the force of gravity pulling down this way. Now, if I know this angle here is 27 degrees, we can actually figure out the amount of this force here and this force here. So remember, what we're going to do is we're going to take this component and I'm going to move it down here. And in fact, let me do this. I'm going to use a different color actually so I'm going to use this. I'm going to move this right here. So that's this moving down here. Make a little note, force of gravity parallel. So all I did was move this down here to make our right triangle. This is going to be our right angle right here. And so now I can solve for those, right? So let's try and do the force of gravity perpendicular first. So that's this side of the triangle. This is going to be my hypotenuse here, which is 441, and this is my angle 27. So force of gravity perpendicular is going to be adjacent to this side. So remember our SOHCAHTOA here. SOHCAHTOA. If I'm looking at the adjacent side and the hypotenuse to that angle, so adjacent side to the angle and the hypotenuse, adjacent hypotenuse, that's going to be the cosine function. So cosine of 27 degrees is going to be equal to the adjacent side, which is FG perpendicular, divided by the hypotenuse, which is 441. So that means I would have to take 441 times the cosine of 27 degrees to get this value here. So if I were to do that, force of gravity perpendicular then works out to be, let's see, 393 newtons. So that's my, I'll make a note over here. So this is 393. That's how many newtons pulls the kid to the surface of the slide. And then now we'll do this other one here, which is going to be this force. So this is opposite that angle. So opposite and hypotenuse is what I'm going to use here. So opposite hypotenuse, that's the sine function. So sine of 27 degrees is going to be equal to the opposite side, FG parallel, divided by 441. So now in this one, it's going to be 441 times the sine of 27 degrees. And when I do that, the force of gravity parallel then works out to be 200 newtons. Okay, so now I've got this force here, which is 200 newtons. I've got this one's 393. I've got this one's 441. Can we figure out any other forces based on that? Well, I know that this force and this force need to be equal. So this 393 newtons here needs to be equal to this normal force, so I do know that one as well, 393 newtons. Now, in this case, I can't assume that that force of friction and this force of gravity parallel. It doesn't say that she's going at a constant velocity. In fact, we can kind of assume she's going to be speeding up because the problem says she starts from rest and it wants us to figure out how fast is she going when she gets here. So we can assume that she's going to be speeding up going this way, increasing her speed, accelerating. So in this case, I don't know what that force of friction is because I can't assume it's going to be equal to that. So we're going to have to remind ourselves of a couple equations that we've already learned. So the first one is, we've got Newton's second law. Net force is equal to mass times acceleration. And then we also have force of friction is equal to the coefficient of friction times the normal force. Now the other thing we have to keep in mind is that for this, if we know we're accelerating down the slide, that means we know that this force needs to be greater than this one, right? And my net force is going to be this way. So the other equation that we're going to have to know is that the net force, the net unbalanced force is going to be this way, or in other words, it's going to be equal to Fg parallel minus my force of friction, right? Because this minus that is going to leave me left over with some net unbalanced force down the slide. So these are my tools that I have to use then to solve this. So I'm going to have to give myself a little more room here. So the first thing I can do is I can actually solve for that force of friction, can't I? Because I know the normal force and the problem gives me the coefficient of friction here. So I can actually figure that out. So let's do that first. So the force of friction is going to be equal to that mu, 0.23, times the normal force, which we already figured out, which is 393. So times 393 newtons. All right, and that works out to be, if we crunch the numbers there, 90.4 newtons. So now I know this force right here, 90.4. And now, since I know my force of gravity parallel and I know my force of friction, I can use those to figure out the net force, right? So the net force, or the unbalanced force that pulls the kid down the slide, is just going to be the FG parallel, which is 200 newtons, minus that force of friction, 90.4 newtons. So that means the net force pulling the kid down the slide is 109.6 newtons. So the difference between these two, here and here, I'm left over with 109.6, pulling them down. And now I can solve for the acceleration, right, using this right here. So the acceleration is going to be equal to the net force divided by the mass. So the net force was 109.6 newtons divided by the mass, 45 kilograms. And so she's accelerating at 2.44 meters per second squared. I'm still not done, so this is kind of a long problem here. We want to solve for what's the final velocity at the end. So now I'm going to have to bring back my kinematic equations. So I have the acceleration, I have the initial velocity, which is she's starting from rest, 0 meters per second. I also have the distance, it's 5 meters. So I have acceleration, initial velocity, distance, and I'm solving for final velocity is what I'm trying to figure out. So if we look at our kinematic equations, the one that's going to work the best is this one right here. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. So I have everything I need to solve for that final velocity. And so if I plug in my numbers, well, this is just going to go away because initial velocity is 0, so I don't even have to worry about that. It's just going to be 2 times the acceleration, 2.44 meters per second squared, times the distance, 5 meters. Now, this is final velocity squared, so I'm going to have to take the square root of that, because I have to take the square root of that to get rid of that squared. And so final velocity, we crunch the numbers, 2 times this times 5, take the square root of everything, and we get 4.94 meters per second. So that's how fast she would be moving once she reaches the bottom of the slide. Whew, man, that was a lot of steps. That was a lot of work to get to that, but we made it through. I'm proud of you. Way to go.